Hi everyone. So this lecture is going to be on Thomson 5.2. It's a pretty short section, but this will take us into these Feynman diagrams and how to actually think about this matrix element thing that we calculated in 5.1, and then take us into these Feynman rules that we're going to see in the later part of the chapter. So let me see if I maximize this. Okay. All right. So in section 5.1, we found that, if we add up these time ordered, not ordering, ordered scattering, right, where, the first time ordering is that, the particle A is the one that spit out particle X, right, this happened first, and then particle B actually receives it, okay. That's one time ordering. The other time ordering is that particle B is the one that shoots out another particle X tilde, right, just in case they are different particles. And then particle A is the one that receives it. So the propagator goes this way. Okay. What we found last time was that if you add up both of these diagrams, okay, what you get is that you get this, well, at least for scalar particles, you get a matrix element that's just going to be, whatever the coupling constant GA is, and whatever the coupling constant GB is, divided by this Q square minus mass of the exchange particle squared between them. Okay, where this 1 over Q squared minus mx squared, right? That's known as the propagator. Okay, so the factor that's actually true even if we're not exchanging scalar particles. In case of scalar particles, this numerator just get a little bit more complicated with some angular dependency. Okay. Because when you add these two up, you actually don't care, right? Actually, you cannot measure which time order happens. So in quantum mechanics, when you cannot tell which time order things happen, you have to add both of those processes up in amplitude, in this case, the matrix elements. So therefore, when you add them up, you don't actually know which time order you have. So therefore, you draw this x with a vertical line instead, because you actually don't know which one is which. Just remember the Q, right, is the forward momentum of this particle being exchanged, right, whatever that happens to be. Okay. So for the scattering above, right, so you have momentum PA coming in, PB coming in. These are forward momentums, right? Then you have this Q coming out, right, which is actually the momentum of this X particle that we don't know about. Okay. So for scattering, right, this Q is actually the forward momentum of the incoming particle, one of the incoming particle, and the momentum of the outgoing particle for this top half of the diagram. You can actually write it the same way, where Q can actually be written as, well, using momentum B down here and momentum D down here, right? If you have these two coming together, right, you have an equation that momentum B plus Q, right, equals to PD. So therefore, Q is actually PD minus PB. Okay. So you have two different ways to calculate the same thing, depending on which variable you use. One will be better than the other. Okay. So that's for the scattering case. If we have an annihilation process where you have some particle coming in, let's say an electron, and then a anti-electron, a positron coming in. So that's why the arrow's drawn outward, right? They annihilate at this point, produce a something. In the case of E plus E minus, there'll be a photon, and then some other particles comes out on the other end. Okay, this is an annihilation process. Okay, the forward momentum in this case, right? You have momentum P1 coming in, right, and then you have P2 coming in. Okay, so this arrow indicates the particleness, but this arrow represents the momentum coming in, because it's actually a anti-particle moving backward in time. So you think about it as a particle moving forward in time. Okay, this momentum actually goes out here, right? This Q is actually the sum of these two momentum added together instead. Okay, So in this case, it's actually P1 plus P2, right? That added together, that gives you that Q. Similarly, on the other side, this is even more symmetric. This Q, this whatever this momentum of this Q is, right? It'll just go out into two different particles, okay? So just be a little careful, right? These arrows, right, represents whether or not you have particleness coming into the vertex or not. Okay, it doesn't actually necessarily indicate the momentum of the particle that's coming in. Okay. All right. So in the case of this annihilation process, the Q square, right, is actually known as the S channel process because Q square is actually equal to this S, where S is this Mandelstam variable, right? Right. Be a little careful, right? I think I remember some people on the exam, right, having trouble with this, saying that S is equal to Q. S is actually equal to Q square. Unfortunately, the square doesn't, they Q and S don't have the same units. Okay, S actually have a units of GeV square. Okay, and we're going to go through a little bit of exercise just to remind everyone how these Mandelstam variable works because they're going to come in very useful as we do calculations later. Okay, so and so remember that when you do a four momentum, so Q, right, is equal to P1, well, Q square. Let's just calculate that. Let's just write Q. Okay, Q is equal to P1 plus P2, right? So that means it's actually equal to the energy of particle 1 plus the energy of particle 2 plus the spatial component is the 3 momentum of the particles, right? So just be careful. These are 4 vectors that you're adding, even though they just look like regular letters. So therefore, right, Q square, right, is actually P1 plus P2. And if you write out the covariant and the contravariant like this, right? So when you do the Einstein summation notation, right, then you have the energy part squared and minus the spatial part squared, right? 2 squared, okay? Right. So that's where this comes from, okay? And the homework, what we'll do, we'll go through what we did. I think it was chapter 3, where we switched to a center mass frame so that you can actually find that the momentum, the momentum of these particles adds up to 0, and therefore, right, the S channel process is always going to have the energy square being bigger than the momentum square, okay? Because this part is not Lorentz invariant. These two things are not Lorentz invariant, right? So they could change between the two, but you can actually always prove that the energy part is always going to be bigger than the momentum. This is known as a time-like process because remember when you're writing 4 vectors, right? P, mu, right? Energy, and then the momentum. This is correlated to how we write the coordinates, right? Where the coordinates is time, and then the 3 spatial coordinates, okay? So the energy is always connected to the temporal coordinates of temporal part of the coordinate system, and then the momentum is the spatial part. And that's why when the energy part of your 4 momentum dominates, it's bigger than the spatial part, we call that a time-like particle, okay, or time-like system when you have multiple particles together, okay? And then in the T channel scattering, okay, we're going to find that the momentum is going to be bigger than the 3 momentum is going to be bigger than the energy part, okay? Therefore, correlating this with the momentum with the space part of the coordinate system, right? We're going to call this the space-like processes. Okay. The next section, next little subsection here, 5.21. I thought Thompson's going to give you some homework to play around with this, but he didn't. So I'm not sure if I'm going to come up with one or not, so that's to be determined. I'll work on that today. But just to discuss what he's trying to get across, okay, so far what we found was that this MFI thing, right, for a scalar particle, so that determines these GAs and GBs, right, is going to be these coupling constant. If they are the same coupling, then they'll be G squared, right, over this propagator thing, okay. What we want to do is actually get some classical intuition about what these quantities actually represent, okay. So we have some slow electron scattering off a proton, right? So usually you have some plus charge here, and then maybe you have an electron that's coming in, and very slowly, right? The electron will be attracted by this proton, and then they scatter off a different direction, right? Okay, right. So in the calculations, which is the one we're doing, which quantum electrodynamic, it should reduce to their non-relativistic result. Non-relativistics meaning, right, the speed of that particle is much less than the speed of light, which is what you actually usually see in classical mechanics. Okay. When you do this calculation, where let's say, right, if you want to calculate the matrix element, right, instead of the squibbly, we get just a regular bold M. Okay, so this is the non-relativistic matrix element. Okay, you can do the same calculation where you have this bracket of around the potential from some initial state to some final state, right? You do the calculation the same way where you plug in the wave function, initial and final, right? So these will depend on the directions, right? This will depend on P final. This will have P initial. Okay, and this potential between the two is actually known as the Yukawa potential, where it's basically going to be the coupling constants between the two vertices. But in most cases, this will just be the electron, the elementary charge square, and e to the minus im, where m is the mass of the particle exchanged. Okay, and r is the distance of the closest approach, right? This distance between the electron and the proton. Yeah. Actually, it's not the closest. So because this potential actually changes with r, so you actually have to just integrate this. I think it comes out to be kind of like the average. So it's actually not the closest approach, okay? Because you're just integrating over all space time, so you get the average distance between the electron and the proton. Okay. So in the limit of this Yukawa potential, where let's say you have the mass of the exchange particle being 0, because right in electromagnetic scattering, the particle being exchanged between the two is actually a photon, right? And the mass of a photon is basically going to be 0. Okay, and so you can actually compute this and then convert this to basically to the Coulomb potential. So maybe we'll do that in the live session tomorrow. Okay, where you can actually do this approximation where you just have where you plug in m equal to 0, and then you'll see that it reduces to the Coulomb potential. Right? Let's see.